you going live now?
Yes, we are. Hello, everyone. Welcome back to the second edition of CLEAP Security Conference, CLEAPCon 2022. We started this conference to raise awareness about cybersecurity in the community. Since then, we have been bringing a lot of industry leaders, experts, researchers, and from academics to share their knowledge with us. Today, we have been joined with a great personality among us, Petrus, and I would let Pooja introduce him to you.
Thank you, Shivani. So let's welcome our next speaker, who is a mathematician and a machine learning enthusiast who is interested in digital activism as it relates to privacy and computer security. Currently, he's the CEO of Axiomata Technology and a partner with more than 12 consultancies across the globe. So we are happy to have you here.
Thank you very much. Thank you, Shivani and Pooja. Okay. I'll briefly remind you of my topic, which is quantum cryptographic algorithm and error of prime. My name is Peters, and I'm the CEO of Axiomata Technologies. And the introduction, the state-of-art classical public key crypto system are based on RSA algorithms, and some of the algorithm are a secure hashing algorithm, and we have Blowfish and so many other algorithms that run the cryptographic space. But at each stage of computational complexities, a certain upgrading of those algorithms are required. For example, 5-6 years ago, MD5 would have been appropriate for some web application. But at this moment, an MD5 cryptographic algorithm might not be appropriate, as it is just an encryption algorithm and not a cryptographic algorithm. So there is an evolution in cryptographic system in the computational world, and every system is bounded to converge at a quantum state where we envisage a more diverse and a more secure environment for computing. And then for this study, we are going to look mainly at quantum key distribution algorithm and the theoretical basis for which it serves as a computational standards for developing a secure communication tool. And then this study has been implemented at the basic level in a control experiment in our lab. We use the QSkit compiler tool from IBM, and then we perform recursive compilation with a minimum of CNOT, and then with all 3 evaluations that we did on a cloud hardware, and then we noted some of the differences, some of the discovery we had about how this system is evolving and how quantum computational algorithms could alter our privacy and security in the next 5 to 10 years. Related work, we have NISQ computer, which promises computational advantages for practical application. In my references 16, 25, and 31. And then we have absence of quantum correction errors on these systems, but it does not mean as the system gets larger, there is no possibility of errors occurring. And then we see that as systems evolve from small to big in quantum computation, there are likelihood of errors happening. But is it possible to minimize these errors? Can this error converge to a point, practical point, where they are computational efficient to be solvable? So we test them with various theoretical techniques to see possibility of achieving this. Now we have our first hypothesis that we are treating these errors that occur in quantum computation as primes. And then we consider a formula where we can easily forecast errors in quantum cryptography algorithm. And then this error, as they perform on computational system, we see the performance of variational quantum algorithm type in near optimal states and their performances. But the variety of noises cannot be forecasted from this point. And then we do not know the causes of this noise, either it be from the computational efficiency or from the algorithm efficiency on its own, or if it be from the kind of hardware that are interfacing the system, we cannot tell at that point. But we consider a typical scenario whereby the hardware is super efficient and there can only be two kind of noises or leakage in the qubit gates, observing that these noises can be estimated in variational quantum algorithm. Then furthermore, we benchmark the influence of this noise in the VQA in real-world learning task, and then the result that we see, we try to fit it in a graphical sense and how we can make sense of it. Now, what are the benchmark data that we have? We have data set from Google computational method and their approach to quantum computing technology or cryptography, as you have seen. Then their optimization algorithm operates 53 qubits. A qubit is the unit of system for quantum computing. Now we all know that a system has higher instability as the qubits increases, and then we see that the error of prime or noises that it can generate increases with this rate too. Then these circuits are finely distributed with a mass core grid, and it has Sherrington Kirkpatrick 3 regular inputs. Then the names of algorithm, here we have one, the benchmark algorithm has about 1 to 5 layers. The 1 to 5 layers will generate optimally about 120 circuits, and then it can hold computation of that average between 0 to 53 qubits. Now, if we check this system now, we see that it has ability to generate a closed computation. In topological space, we have an example of a closed space with open subset. Then a quantum system mimics something similar where there are open subsystems in a closed space, but they have computational efficiency, but it's not infinite in the sense that when this computational efficiency approaches their limits, it can generate errors, random errors. But these errors now, how are we relating these errors to prime numbers or to prime algorithms? So we look at the rate at which qubit states are generated in quantum computing system. Now, if a quantum system generates a qubit, if it generates a computational power that can reach qubits smoothly and increasingly at each stage, then it has a computational efficiency that it is capable of correcting its quantum errors. But if the computing efficiency does not increase as the algorithm executes, it is possible to throw out random prime errors. Now, we check capacity of any computing system. That if we have quantum computers that are connected in parallels, and we say they have infinite computing capacity, then we are assuming that the system has an efficient algorithm to power infinite computation. But supposing we have another system that does not have infinite computing capacity, let's say it has subsystems that have finite computing capacity, but they are limited by efficiency of an algorithm that computes for each qubit state, then we are limited by one, the scheme of the superconducting qubits that combine two microwave techniques, and then applying shelving techniques to the qubit that effectively increasing energy relaxation time, two-tone excitation state of the reader resonator to distinguish qubit population in higher energy level. We can first of all state that the computing system is close to efficient, but it does not guarantee us that we can have a very secure system. Then we take a look at another key issue, which is the law of large numbers, that prime numbers are likely to converge as we progress in sequence. But the implication now is, do we have capacity to exploit too many prime numbers at close to efficient states in quantum computing? If that is possible, do we have any other possible technique that can crack the already existing algorithm within most efficient time with using quantum computing systems? Then it is possible to say that we have systems, operating systems, that communicate with so many quantum systems, and then they have efficiency to give an end user a computational power that is capable of unraveling some of the hidden mysteries in encryption and cryptography. Now, how do we relate this with prime numbers and prime errors? Two, how can this be of any use in modern system? And three, how does this evolve in near-term computational efficiency? Now, I'll start to explain one concept about operators pumping and quantum state bosonization. For example, now, when we have a near quantum efficient state, we see that their operations, their communications are in order of primes. Two, the effectiveness of such communication does not matter to the computational system. It matters to the end user who desire information from this system. And then we now depends on the output that this system is capable of giving us. And if this output is meaningful or meaningless at the end of the day, it does depends on the user of this quantum computational system. Then number three, now we look at how this evolving system can be very useful in the near-term future. Does bosonization of quantum state contribute to securing privacy standards, to securing encryption standard? The answer is yes, the answer is no. From what we have seen, it is possible to use this quantum dynamical system to buffer encryption algorithms to help protect privacy of computing systems. Then, if photons are able to communicate with each other in near efficient states, meaning could be read out of these systems, and then we could have various interpretation, and then converting these systems from being just mere threats to computational system to protecting entire privacy of the computational system could become achievable in the nearest future. This diagram is an example of how communication can be achieved between boson states in the quantum field. But this communication does not make sense if it does not come out as a readable output for the end user. And thus, we concentrate on the outcome of this process in the short term. Okay, by computational basis, we have states, multiple states, efficient state, inefficient state, and we have close to perfect computational state of a quantum dynamical system. But if the errors that this system can generate in order of prime surpasses its efficiency, it may not be helpful in protecting privacy and the computational system as we have envisaged for quantum computing. And thus, there are ways that would be possible to still breach this system in the long run, which will unfold to us as individuals start having their own quantum computational capacity. And then, for example, we have people having access to cloud system, which can be used to execute very large scale computing capacity. Though those are not near term in quantum computing states yet, but they are very efficient, and we can use them to simulate what is likely obtainable in the nearest future. For this, we have a computational basis as a measurement that takes a higher energy. For example, if we have a natural output, the leakage of the system is proportional to error of primes that are observable in the topological space. And for those that have some background in mathematics, this is an example of completeness in a topological space where we have a second rule that dictates completeness in a topological space. And we can see this, that if this error propagates in a quantum state, we have too many incomplete states that can easily generate noises in order of primes. And this noise is not good for the system as it dictates inefficiency for the system. And thus, can we relate quantum computing cryptographic algorithm efficiency to prime numbers? Yes. One, how do we do this? If the noises that are generated by any quantum computational states are proportional to prime numbers, then we can say that the error of primes in that system is proportional to the most efficient qubits that the system can give the end user, or the system can put to most efficient use given any algorithm. But now, if an efficient algorithm is used in generation of qubits, in generation of cryptographic output, it is possible for us to determine how efficient a computational system could be at the end of the day. But in this research, we are trying to find out that as cryptographic algorithm converges to near efficient term, it is possible to have error due to, it is possible to have prime errors that are generated by noises. And these errors can be purely deduced or can be purely understandable by distributions of prime numbers in the quantum computational states. And as thus, we are researching further to see how group theory, how law of large numbers can help us to boost our understanding of quantum computational states where large numbers are occurring and where we can have weaknesses, where noises cannot be understood ahead of time. Because when I began this discussion, I said that we are looking at a system where the noises cannot be forecasted in near term, but quantum states does will allow you to check if possible sources of errors are available, but they may not describe the noises to you in detail, and then you might not be able to understand how these errors occur. But when an algorithm is is not efficient, is not close to efficient for the quantum state, we see that these noises constitute threats to cryptography, it constitutes threats to privacy of users, and it constitutes threats to people who are going to adopt them in the long term for computational purpose. But it is nothing to worry about yet, as as quantum computational power has not been, it is not going to be very available to end user over the next 5 to 10 years yet. And before then, we hope to achieve smooth computational efficiency in quantum states that will enable users to compute safely and then to enjoy their privacy as it is. And as thus, I try to bring this very short treatise to an end with a few references, and then I'll try to close with a little remark that quantum computation will have a very big impact in the mathematical space and in the field of securing individual privacy. And as thus, we need to research more on how we can relate the convergence of quantum computing, quantum cryptography, and the mathematics behind it, so we can unravel the benefits that we all share in the next few years. Thank you very much.
Thank you, Peter, so much. It was indeed a very insightful session. Thank you for the presentation.
Thank you very much. Thank you. Did I take more than 20 minutes?
Yes.
Whoa. Thank you.
We were right